Hey everyone, this is Muhammad Nadeem and welcome to my YouTube channel. Today we are excited to discuss about Coulomb's law. In previous class, we explored the concept of electrical charges. And saw that there are two types of charges. One is positive charge and the other one is negative charge. And we also know that these two charges originate due to the friction between two bodies. Now I am going to take two charges. Let's say I am taking one positive charge and the other one is also positive charge. So these two charges having same nature. Therefore, we call them like charges. And as you know that these two charges are positive and like charges, therefore there will be the force of repulsion between these two charges. So between the like charges we have force of repulsion. In the same concept, if we take a positive charge and and on the other hand we take negative charge, now these two charges do not have the same nature. Therefore we call them unlike charges. Now here will the force of attraction between these two charges, because this is the positive charge and this is the negative charge, and there will be the force of attraction present between these two charges. If I consider two scenarios, one scenario, in first scenario I take one positive charge and also take a negative charge here. So this is actually positive charge and this is the negative charge. And we say that we know that there is the force of attraction between these two charges. And let's say I label that as F1. And the second scenario I take the same example, but here I take two positive charges, one this positive charge and the other one is this positive charge, and take the same negative charge here. Now the force will be different from the first scenario, because here the number of charges increases. So therefore I call this F2. So from this we can say that F2 is greater than F1. So here these two scenarios actually explain that this force between the charges actually changes. So similarly, these are changes with the charges. By changing the charge and an object, the force between by changing the amount of the charges, the force between them will be changed. Similarly, I take the second scenario that if I consider one positive charge and it is away from the other negative charge. Here the distance is, let's say, in macroscopic level, let's consider it is 0.25 meter. Okay, so and on the other hand I take the second scenario. This is actually the first scenario and this is the second scenario. I take now here this is the space, so here I take the same positive charge and now take the negative charge here. So this is actually the negative charge and this is the positive charge, but in this case I have increased the distance between these two charges. Before, in this case, we have such a distance which is let's say I consider 0.25 meter, but now it is 0.5 meter. Actually the charges, the distance between the charges are not so high, but I consider that in macroscopic level in order to understand you in better way. So here now I increase the distance between these charges, the same charges, but I increase the distance between these charges, and also I label here this is F1 and this is F2. Now from these two scenarios, can I say that the forces between these charges, which is positive and this is the negative with distance 0.25, will be different from this force, because there is the distance has been increased. So here from here we can say that F1 is greater than F2. So from this whole discussion we can say that the force is actually changes, and that changes is actually occur due to the charges. Okay, in this case this force occur due to the charges, and in this case this force occur due to the distance between the charges. So the relation of actually the relation of force with charge, actually I am taking Q as a charge, and also the relation of force with the distance, and in this case I take the distance as R, is quantitatively discussed by Coulomb's law. This is quantitatively discussed by Coulomb's law. This is the basic simulation for the Coulomb law. In this simulation, we will graphically represent the relation between the force and the magnitude of the charges, and also the relation between the force and distance R between the charges. So let's introduce the interface of this simulation. Here in this interface we have two objects. One is this object which is labeled as A, and on this object there is large number of positive charges. As mentioned here, the charge on object A with a unit of Coulomb and 10 raised to the power minus 4 is actually equal to 10. So the number of positive charges is 10, and this 10 multiplied 10 raised to the power minus 4 Coulomb, and the charge on this object which is labeled as B is in this case the charge on object B is minus 10 multiplied 10 raised to the power minus 4 Coulomb. So this object have positive charges, okay, and this object have negative charges, and we know that there is a force of attraction between the positive charges and the negative charges. In the other word, we can say that the negative charge will exert force on this positive charge, and similarly this positive charge will exert force on this negative charge. So there is some force. In this case that force is attraction, so there is a force of attraction between these two unlike charges. So the Coulomb law actually quantitatively analyze that force which is present between these two objects. In this case, there is a force of attraction between these two objects, which is labeled as A. If, okay, it means that this if here will depends on the distance between these two objects, that how these two objects, how far these two objects are present. If these two objects were present near to each other, the force will more. So this force is depend on the r, which is the distance between the objects, and this force is also depend on the magnitude of the charges present on the object. Okay, the magnitude, the number of the charges present on the objects. So this force is also depend on Q, charges. So from this theoretical explanation, we can graphically represent this. So and graph this relation, the relation between the force and the distance r is labeled here. If you check this box, the graph will turn to the relation between the force and distance r between the object. And if you want to plot the relation between the force and charge, so then you will check this box. Okay, so here we can say that the force depend on the distance r, and also this force is depend on the magnitude of the charges present on these objects. Okay, in this case we will plot the graph between the force and the distance charge and the charge. This charge is actually the charge on these objects. Okay, if I increase the charge on this object, the force between them will also increase. Is here and if we decrease the charge on the object, okay, the force between them will also decrease. So here we can say that we can see that if I am going to decrease the charge on the objects, the charge on the objects, the force from here also decrease. Is I am going to decrease the force, the charge, the force also decreasing. Okay, and this is the graph, the graphical representation of the relation between the force and the charge. That relation is actually this linear form. This is the linear. It means that the F and Q are linearly related, mean that they are directly related. So from graph we say that F is directly related to Q. Q is actually the charge on these objects. Okay, similarly we will turn the graph we will turn the graph from the from the Q to the R. Here in this graph we will discuss the relation between the force F and the R. R is actually the distance between these two objects. These two are objects, these two charge objects. If I decrease the R, mean if I decrease the distance between these two objects, the force will increase. As I am going to decrease the distance, due to which you have to focus here on this graph, due to which the force is increasing. If I decrease the R, mean I am going towards this origin, toward the zero, mean the R is decreasing and the F is increasing, because the graph is now moving upward. Okay, so if I decrease the distance between these charge object, the force is increasing. So in this case you see that if I decrease the distance between these two objects, the force is increasing. Okay, and the graph give us this relation. Now the name for this relation is parabola-like structure. So in this case the relation of the F and R was inverse, but in parabola form. Okay, this is the parabolic form of graph. So here this is actually parabola, and this parabola in mathematics comes from the quadratic equation. In quadratic equation, the higher degree of polynomial is actually is equal to 2. The higher degree will be 2. Therefore we can write this relation between the F and the R as F is inversely proportional to R, but with the square of the R. This square is due to this parabola nature of the graph. Okay, we have two relations. One conclusion was F is directly proportional to charge on object A, and it is also proportional to the charge on object B. So F is directly proportional to Q1. Qa is Q1 is the charge on object A, and Q2 is the charge on object 2. And the second conclusion was this: F is inversely proportional to R square. So combine these two. F is common from these two. Proportionality constant, we take one of them, Q1, Q2, and now that is divided by R square. Here simply I combine these two. Now we know that whenever we replace this, we will write equality sign and constant for this proportionality sign. So this become F is equal to K equal, and K sign is actually for proportionality sign. So F is equal to constant Q1 Q2 by R square. Okay, and this is called this is actually the Coulomb law. This expression is actually the Coulomb law. Okay, this is the Coulomb law. Now we will discuss what is this K. Okay, here in this Coulomb law, what is this K? So K is actually the dependence of the environmental condition. Here K is equal to 1 over 4 pi epsilon naught. In this case, we consider this experiment is conducting in the vacuum, and the permittivity of the vacuum is epsilon naught. Here the value of epsilon naught is approximately equal to 8.85 multiplied 10 raised to the power minus 12 Coulomb square per Newton per meter square. This is the value of the epsilon naught. Okay, so this is actually for the vacuum. This is actually for vacuum. So for vacuum, the permittivity of that pre-space is actually epsilon naught is equal to 8.85 multiplied 10 raised to power minus 12 and this units. So put this k value here in this Coulomb law, so that Coulomb law become if is equal to, we will put this value instead of k 1 over 4 pi epsilon naught q1 q2 by r square. Okay, this is the another simplification for the Coulomb law. Now what will happen to this equation if we put other medium than a pre-space? Because here this epsilon is only for the pre-space, so for the other medium we will put not epsilon naught. We do not put epsilon naught, but instead of this we will put only epsilon value. Okay, this is actually for free space or for vacuum. Okay, and if there is other medium not a vacuum, then what will happen? In that case, if medium will equal to 1 over 4 pi epsilon, this is epsilon is for other medium than the pre space, epsilon q1 q2 by r square. Okay, and this is the equation of the Coulomb law. This is actually the Coulomb law for the medium. Okay, we can also simplify this law furthermore. As we know that relative permittivity is the permittivity of the medium divided by the permittivity of pre-space. So from this equation we can conclude that epsilon as permittivity of medium is equal to epsilon naught permittivity of pre-space and epsilon r the relative permittivity. Okay, so we have to put this value of the epsilon in this equation. Okay, so that equation become f of medium is equal to 1 over 4 pi. Now instead of epsilon we will put this value epsilon naught epsilon r. Okay, and the rest value will be put here q1 q2 by r square. So let's simplify this equation further as if medium is equal to 1 over 4 pi epsilon naught q1 q2 by r square, but one thing is remain, which is 1 over epsilon r. Okay, let's I have simply rearranged this equation. So here you have to focus on this as we prove here this equation, this relation, okay, and this relation is same. So instead of all these we can write if vacuum. So for that we have to write this if medium is equal to, instead of this now I will write if vacuum multiply 1 over epsilon r. So the final answer, the final equation become if medium is equal to if vacuum divided by epsilon r, and this is the final equation, sorry, this is the final equation of a force between the charges in any medium. So for every medium there will be every medium have a specific epsilon r value, and from that you can find by the original, the new medium, the force in the medium will be calculated by the force in vacuum divided by the permittivity of that medium. So this is all about the Coulomb law, and this is the all about the Coulomb law in vacuum and the Coulomb law in medium.